Hello, I'm John Gustafson, and this is Charles Schorb, and this is a replica of the first electronic digital computer, the atanasoff-berry computer. The atanasoff-berry computer, or ABC, was built at Iowa State between 1939 and 1942. This replica was completed in 1997. Using this replica, we will take you through a complete example of using the machine to solve a set of equations. Each of these vacuum tube assemblies does the arithmetic for one number. You can see 15 of them here, and there are 15 just behind them. The construction is modular, like it is in modern computers. The modules operate in parallel, so the ABC was not only the first electronic digital computer, but the first parallel computer as well. The ABC can hold two equations at once, one on each of these drums. The ABC was the first computer to use binary digits, or bits, to store numbers. The bits are arranged in columns on the memory drum. You can see 30 columns on this drum, and each column has 50 bits. So the entire storage of the computer is 3,000 bits. That's about a third of a kilobyte. To solve a full-blown set of 29 equations and 29 unknowns would take about 25 hours. So for purposes of this demonstration, we'll just solve two equations and two unknowns, the ones shown here. 2x plus 4y equals 8, x minus 3y equals minus 11. The first step is to enter the data into the ABC. There is no keyboard for data entry, so you have to punch the numbers in on cards. These punch cards are the same type that were used until the 1970s for getting data into a computer. Our first equation is 2x plus 4y equals 8, so we punch in the numbers 2, 4, and 8. You may have also noticed that we're using only whole numbers. The ABC did not use floating decimal points, so you scale up the numbers until everything is to the left of the decimal point. That took about a minute. While we're at it, we'll make the card for the second equation as well. For x minus 3y equals negative 11, we enter 1, minus 3, and minus 11. Notice that to make a number negative, we type a 0 for the first digit. If it's blank, it's assumed positive. Now we're ready to read in a card. We type the numbers in decimal notation, but the ABC works in binary. We convert the decimal numbers to the bits that the computer uses for calculations by use of the base 2 conversion drum. This is a different kind of memory drum. These pegs represent a table of binary numbers. When a peg touches a brush, it produces a binary 1. If there's no peg, it means a binary 0. Now we'll turn the ABC on and enter the data with the base 10 card reader. This meter should read plus 120 volts and minus 120 volts when everything is warmed up and working correctly. The machine draws less than 1,000 watts of power, less than your typical hairdryer. It plugs into any wall outlet. Now we'll turn the motor on that keeps the drums spinning. A power train keeps the memory spinning, just like the motor of a disk drive. It also produces a 1 cycle per second clock to synchronize everything. The motor is synchronous with the 60 cycles per second from the power outlet. The drums rotate once per second. The 50 pegs, one for each bit in the number, pass by brushes at the same rate as the 60 cycle per second line turn. That leaves 10 cycles blank, and you can see the blank part of the drum. This was the first dynamic memory. Inside the drum are 1,500 capacitors, one per peg. Capacitors store a voltage to represent a bit and get refreshed once per second so the charge on the capacitor doesn't fade away. The first thing we're going to do is make sure all the memory is clear. The operator console has a switch to clear the memory, and after one revolution, everything should be set to 0. The card reader is mechanical. The reader mechanism moves while the card sits still. Every time a brush passes over a hole, it makes contact with the brass dots under the card, and that completes a circuit. Each brass dot connects to a brush that reads the conversion drum. It's hard to see now that it's moving, but the pegs on this drum form a read-only memory. It's a table of binary numbers that correspond to every possible hole in the IBM punch card. So for the number 11, it reads the 1 in the tens column, looks up the number 10 in binary, and sees 1010. Now the ABC vacuum tube logic adds that bit pattern to what is already stored in the rotating drum. The card reader brush has read the digits and converted them and added them as well. Some things happen 30 at a time on the ABC, and some things happen 5 at a time. Since the ABC doesn't have a modern computer display, we've hooked up a digital oscilloscope that shows what's on the drums in binary. If you're not familiar with this kind of oscilloscope display, it represents numbers with on-off bits, this being off and this being on. The number 8, 4, 2, 1 in binary, if the 8 and the 2 were on, that would mean the number 10. If all 4 bits were on like this, it would mean the number 15. The operator now tells the ABC to copy those 3 numbers to the other drum for safekeeping. He then clears the first drum to receive the next card. We'll now enter the top equation. We entered the bottom one first so we can use the top one to eliminate a variable in the bottom one, just like you do when you work this kind of problem by hand. But you can do it either way. Like many computers that came later, the ABC speed is limited by the time for input and output. Each decimal takes 1 second to read in, so it takes 15 seconds to read in all the numbers on a punch card. We can save some time by working with smaller numbers and starting the reader at the first non-zero digit. With the number loaded, we're ready to solve the equations. The ABC eliminates x from this pair of equations by subtracting the second equation twice to give 10y equals 30, or y equals 3. If you know how to read binary off an oscilloscope, you can see the 10 and the 30 there. Let's read the number out using the ABC. To read the number out, we reverse the conversion process used to put it in. Punch cards are used as masks to select which number we want to read. This masking card selects the second column, which should have a 10. The output is like the odometer on a car, except that the digit wheels are independent. Decimal values from the conversion drum are subtracted from the number in memory, and this solenoid kicks the wheel by 1 digit until the subtraction makes the number change sign. Then the same mechanism that pushed the card reader moves to the next column and starts adding numbers. It alternates between adding and subtracting, and that's why the dials are numbered in alternating directions. The number 30 should still be in the computer. A different mask lets us read that out. We reset the odometer mechanically. That completes forward reduction of the equations. If we had done that using a large number of variables, we'd be happy to do this last bit of math by hand. 10y equals 30 means y equals 3. Now we back solve using that value for y. Both equations were altered by the operation of the computer, so we need to put the first equation back in. We also put in a new card that has this value for y. Since we're now eliminating y, we have to change the jumper over to the second coefficient. The larger the numbers, the longer it takes for this process of eliminating one variable. For 15-digit precision, it can take about 2 minutes just to do the elimination. That's still a lot easier than doing it by hand, and less error-prone. The ABC now can use the y equals 3 and the second equation to solve for x. By adding this equation 3 times, we obtain x equals minus 2. This light shows that the answer is negative. Now, we'll read out the values that determine the final value of x. You may be thinking that this is a lot of work to solve equations, and that you could do it as well by hand. But every time you double the number of equations, it takes 8 times more work. So before the ABC, no one even thought about solving systems as large as 10 by 10, say. Atanasoff wanted to solve problems in physics and statistics and mechanics that always got bogged down in solving the systems of equations. Everything else you could pretty much do by hand, slowly. 2 equations fit on the 2 memory drums. If we had 3 or more equations, we'd need a fast way to save the intermediate work. Atanasoff and Berry invented an electronic recorder that could put all 1,500 bits in a drum onto a piece of stiff paper. High-voltage arcs punch holes in the paper to show where a binary 1 is in the machine. For writing, the electrodes are pointed. The bursts of high voltage are provided by these banks of thyrotron tubes. They give off a violet flash when they operate, unlike the tubes that are used for arithmetic. When the operator pushes the console button, a cam is engaged that pushes the paper through rollers and past the electrodes. The holes are very small, but if we hold the paper up to a bright light, you can see them. This completes the demonstration of the atanasoff-berry computer on a simple problem. It took about 6 minutes to solve a set of 2 equations. It used binary logic, parallel processing, 15-decimal precision, a system clock, and dynamic memory. Modern computers are over 1 trillion times faster, but their underlying principles of operation are the same as in this 1940 computer.